Okay, this is the Franck Hertz experiment, and this is a wonderful experiment that exhibits the fact that the energy levels in the atom are discrete energy levels. This experiment was done. Oh, I think that Niels Bohr published the Bohr atom about 9 months before this experiment was published. It's a really beautiful way to show that energy levels are quantized. I think you can look this up historically. Einstein, when he saw it, it said it's so beautiful it almost makes you cry. I think that's what he said. You can always look that up. But anyways, the experiment's actually, I have the entire schematic for the experiment right here. Again, it shows that if you have a positively charged nucleus, as you know, an electron in an inner orbital can get knocked out to a higher orbital by a streaming electron colliding with this atom. When an electron is knocked out to a higher orbital, it can fall back into where it was at the lower orbital and emit a photon. And the energy of the photon, which is hc over lambda, wavelength of the emitted photon, is equal to the energy difference between the two energy orbital levels in that atom. The Franck Hertz experiment is basically, it's a glass tube. This boundary is a glass tube, and you pull a vacuum on it, and then you reintroduce, say, an atom like argon in there, and that's what these large black dots are. They symbolize argon atoms. All vacuum tubes have a very low pressure, so that the electrons can travel through the tube. Most vacuum tubes have a low pressure, unless you're trying to make, well, anyways, so the electrons can move through it and collide with the atoms. This conductor right here is so inside here we're going to put argon. This conductor right here is just a filament, a tungsten filament, and right above that is a grid. It's like a screen, so it's a cross-hatch pattern of conductor so the electrons can get through it. And the voltage between this first grid, G1, and the potential that the filament is at is this voltage right here, VG1K. The potential that the filament at is K. So anyways, this negative bias here is going to cause electrons to flow through the filament. And as electrons flow through this filament, the filament heats up, and the thermodynamic heat in the filament causes the electrons to, those phonons, which are vibrational, they're actually quantized vibrations in the solid, knock electrons out of the conduction band and literally out of the metal. So the energy of a phonon can get to equal the work function of the metal, and you pop electrons out. Then the grid G1 is positive compared to this filament, so it sucks electrons to it and through the grid. Then, so electrons get accelerated from here to here, and then there's another grid on the opposing end of the tube, G2, and the voltage between G2 and K is something we're actually going to vary. That's what this symbol here is, a variable power supply. That's a knob we can turn. VG1 is going to be, K is going to be fixed, but these electrons will be accelerated through this potential difference. And as you know, the energy of those electrons traveling through this gas now will be equal to their charge times the accelerating voltage. So that voltage will be G2K here. So the electrons go streaming through this argon gas, and we're going to vary that voltage here from 0 up to some value. Now, as the electrons get through the they're going to reach grid G2 with some kinetic energy equal to their charge times the accelerating voltage. Now they're going to be slightly decelerated from here to here. This is the collection plate for the electrons. That'll be explained in a second or in a minute or so. So they will slow down from here to here just slightly. but they're going to have plenty of energy to go through G2 and get to this plate, the potential which is at potential A here. And those electrons will then move in through this wire, which has an ammeter in it, and give us a current in microamps, that symbol. This is an ammeter, which will be a connection in the experiment. And it's going to be floating at some voltage, some slightly negative bias voltage with respect to this position here, G2. And that's what this battery thing here is. It's a floating potential. In other words, neither plate is connected to ground. Okay. So what happens is, how does this experiment work? Well, it turns out that we're going to put argon gas in there initially. Franck and Hertz actually did the experiment with mercury vapor. But we're going to use argon, because if the tube breaks, we won't get any poisonous fumes emitted into our lungs. Of course, we have lots of smoke in the air these days, but we don't need any additional toxins. So as these electrons go streaming through this argon gas on their way to the collector plate here, they will collide with these argon atoms. And they will collide elastically. In other words, they won't lose any energy. They'll work their way to this plate without losing hardly any energy. They'll undergo elastic collisions with these argon atoms. And when the voltage V, it turns out that for argon, there's an excitation level from an inner orbital to an outer orbital for the orbiting electrons in argon that has an energy difference of about 11 electron volts. It's 11 point something. It's in your lab manual, that number. But when you get, so anyways, when the kinetic energy of these electrons are going from this filament to G2 is about 11 volts, or 11 electron volts, because they've been accelerated through 11 volts, 11 point something. The electrons will have enough energy to collide with an inner orbital electron in argon and knock it up to the next orbital, the next allowed energy state. So for instance, if they only had like 7 electron volts, this electron could not go all the way, and so it's stuck here. There's not an intermediate state because of the quantization of energy. So anyways, as you turn up the voltage here, VG2K, eventually the voltage between this filament and this grid G2 reaches the energy, that voltage times electron charge. That energy is equal to this energy of the gap, and the argon starts absorbing electrons. So initially, there's only elastic collision, so as you turn up the voltage here, Vg2k, the current, the electrons reaching the plate, just increases. Then when you reach around 11 point something volts, right? Let's call it 11. Suddenly, the electrons in the neighborhood of the grid, G2, have enough energy to excite the argon, the orbiting electrons in argon out to a higher energy level, and the argon absorbs these streaming electrons. And then, of course, as these streaming electrons get absorbed by argon and knock this inner orbital electron of argon out to the next higher orbital, then that electron in argon falls down through the energy gap and emits a photon. That 11 electron volt photon is a very short wavelength. It's in the invisible ultraviolet and we can't see it, so we wouldn't know that it's happening. Except for the fact that within the experiment, since these streaming electrons, which are increasing and hitting the plate with increasing voltage, when you get to 11 volts here, suddenly these electrons are being absorbed, and they never reach the plate at A. And so you'll see a sudden drop in the current in this ammeter, and that's exactly what the Franck Hertz experiment shows. When you get to that point here, 11 point something volts, there's a dip in the ammeter current. So even though the actual signal of this invisible ultraviolet would be coming out, we can't see that, since the experiment is set up when that is absent, or when that ultraviolet light's coming out, that's when the electron current in our actual circuit dips, and we see it happening. And so that's quite wonderful, because we get to see it. Then if you continue increasing the voltage here, the accelerating voltage from the filament to the grid G2, if you continue increasing that voltage, oh, by the way, let's say we're just got to 11 volts here from here to here. You can see what these symbols mean here. This plus sign means that this grid is positive compared to the filament, so it's pulling electrons toward it. Then this 3 plus signs for this next grid means that the electric potential there is higher than the electric potential here. So electrons are accelerated from here to here. They're going downhill in the energy curve, being accelerated from here to here. They're accelerated from here to here and from here to here. Then they're slightly decelerated. You see these 2 plus signs here for this electrode. From here to here, they're slightly decelerate. So when they lose the bulk of their energy right here from being absorbed by argon, there's a decelerating potential from here to here, and they slow down, and we can see the dip here. So the experiment's set up to if they lose the majority of their kinetic energy near G2, that they don't make it to the plate. Now statistically, some of them will still make it through, so you can still see a current here, a small current. You see decreasing rapidly here to some minimum. So that's what these symbols, plus, then triple plus, then 2 plus. This means that the electric field from here to here is this way, and so it will pull electrons up. The electric field from here to here is this way, so it accelerates electric. Remember, the electrons are negative, so they suck toward the more positive plate. And then the electric field from here to here is this way. So they're slowed down from here to here slightly. There's a slight potential there. That's VG2A. That's the decelerating potential there. Okay? So anyways, now what happens when you increase past the 11? Well, let's say you go to 22. On the way to 22, so electrons, as you know, the position where they're going quickly enough to excite this argon atom to its next energy level, electrons, the argon atom to the next energy level, if it's exactly from here to here is 11 volts, it'll happen right in front of this grid. But as you increase the potential from here to here, it starts happening sooner. In other words, if the potential from here to here is, instead of 11 volts, it's 15 volts, then the electrons will have enough speed somewhere in here to be absorbed by argon. Okay? And then from here to here, they'll be accelerated, but not quickly enough to be absorbed again by those argon atoms by G2. So you might see it here, but you won't see that with your eye because they'll be emitting UV light at this place. But when you get to 22 volts, or twice the excitation energy here, from the inner orbital to this outer orbital of excitation for the argon. So as you increase the voltage up to 22, then halfway between here and here, electrons will have enough energy to be absorbed. But then so let's say they lose all their kinetic energy right here, so the velocity is 0 right there because they got absorbed. Then they'll get accelerated from here to here, and if the potential difference between here to here is another 11 volts, then they will again be absorbed right in front of the grid and not make it to the plate. So you'll see a second dip here, a second dip at twice that voltage down. And then of course you'll see a third dip at around 33 point something. It's not exactly 11 volts, this excitation voltage here. So this is what we expect if indeed the energy levels in the argon atom are quantized. And indeed, that is exactly the curve we generated in this experiment. You'll see it when we have argon gas in here. Now, and so we'll do that, and we'll generate that curve, and you'll get the data, and you'll play with it according to your lab manual that Dr. Essergen has written up so gracefully. Okay, so this is the Franck Hertz experiment. I think I've identified every piece of it, and I'll show you. VG2K is the knob we'll turn to make the experiment happen. This will be a constant, the voltage between this grid and the filament, and then that voltage there is, essentially the filament, this negative voltage. Okay, so and then of course the ammeter and this voltage here is a bias to slow electrons down slightly from here to here, so that when they lose all their kinetic energy in the neighborhood of G2 before it, they don't make it to the collecting plate, and we see a dip in this electron current here, here, and here, and here. Okay, so that's the Franck Hertz experiment, and we're going to continue now. If we look over to the right here, I have another drawing. Now this drawing here is a close-up of the inside of the tube. This curved line is the filament. I even wrote filament there for you. Just so I can get the circuit components out of here. Now, the second part of the experiment is the second thing we'll show is strictly qualitative, and we change the gas. What we do is we put, instead of argon gas in here, we put neon. Let me see if I have put neon. This becomes neon atoms, and neon atoms have a energy bands within them for the allowed states of the electrons. And if this is a neon nucleus, of course you have negative orbiting electrons in discrete energy levels. And the excitation level is that we're going to see is from this inner orbital out to this outer orbital, and that's about 18.4 electron volts, that energy. There's also an energy level at 16 electron volts. Now, if you knock an electron from this level out to this level and it falls back in, it'll emit a 16 electron volt photon, which if you use that energy in the formula, if you take that roughly 16 electron volts, and you set that equal to hc over lambda, hc you can write hc as 1240 electron volt nanometers, and quickly solve for lambda. That's in your textbook, I'm sure, or your notes. And you'll find out that lambda for 16 electron volts is a very short wavelength photon that's invisible. So if you excited something out to the 16 electron volts and it fell back in, you wouldn't see it visibly. Of course, there's a probability of getting excited from here to here. But when you excite the electron out to the 18 electron volt, through the band gap of 18 electron volts here, between this energy orbital and this energy orbital, this electron that comes out to, through this 18 electron volts can fall back to the 16 point something electron volt energy level and emit a photon, and that photon will only have an energy of 2 point something electron volts, which will have a wavelength in the orange reddish visible spectrum, and we should see such a glow coming out of the tube, such a glow of that color light coming out of the tube. And indeed, that's what happens. So if we run the experiment in another tube, what you'll see is electrons, when the voltage between the filament and G2, which is this VG2K, right, is around 18.4 electron volts, the energy of the electrons that came out of the filament and reached this grid will have enough energy to excite an electron in the neon atom from an inner orbital to this outer orbital across 18.4 electron volts of energy. And then when that electron falls with a certain probability, just a couple of electron volts through an energy gap of 2-point-something electron volts, we should see an orange glow. So when you run the experiment with neon atoms, you'll see the voltage and current increase at around the 18.4 volts. You'll see an orange glow in the neighborhood of this grid G2. You'll see an orange glow. Now, what's really neat is we can continue past the 18.4 volts, the potential between the filament and this grid G2, and until we get to twice that energy for the electrons, which would be, say, 18.4 times 2 would be 36.8 volts. Then when an electron gets halfway between here and here, at the halfway mark, it'll have a kinetic energy of this 18.4 electron volts, and you'll see a lot of absorption halfway between the filament and the grid. And indeed, that's what happens. The electrons that are accelerating through the gas get halfway through it when the voltage from here to here is twice 18.4 electron volts, and you'll see an orange glow. You'll see orange light. You'll see a bunch of orange light. One of these pens works. Right here, you'll see it like a bunch of orange light coming out, in all directions here. So you'll see a band of orange light. We'll have a transparent tube here, glass out here. And we'll see a line of orange light here, and then another line of orange light here coming out. I'm not sure what color this is, but it may not be orange. This is a pen, and I'm colorblind, so you see just want to see that's different than this. That's enough. So at twice this excitation voltage, remember, voltage and energy, if you have a voltage and multiply by the charge electron, that gives you energy in electron volts. So, when you're young, you keep reminding yourself of that, and then it's second nature eventually. So when we reach an energy accelerating voltage between here and here to be twice the voltage, or when electrons being accelerated from this point to this point accumulate an energy in electron volts that is twice the energy gap between the inner and outer excitation orbital, then we'll see an energy a glow of orange light here, and then another one here. And then you can even go to 3 times. You can even go to, hang on, we got to turn our phones off here. When you go to 3 times that voltage, which would be 3 times this number, if we go to 3 times this number here, then you'll start to see, when it gets 1/3 of the way between here and here, 1/3 of the way between here and here, you'll see a glow at 1/3 of the distance, and then 2/3 of the distance, and then way out here you'll see another glow. And so we'll look forward to that when we do the experiment. So the first part of the experiment will show this graph being generated here, the Franck Hertz graph with argon with an argon tube, and then we'll just do a fun thing with neon atoms in the gas, and we'll see these orange glows, these bands of orange glowing light. Okay, so let's go over to the apparatus and do that.